both by limiting pressure and by regulating flow. When pressure is closely matched to the work being done, and when flow is only as great as necessary for the speed at which the work must be done, then horsepower going into the system will most closely match horsepower going out of the system. This relationship between horsepower in and horsepower out is called efficiency. Usually it's expressed as a percentage. Efficiency can be calculated by dividing output horsepower by input horsepower. For example, if a prime mover like an electric motor must develop 100 horsepower in order for the pump to develop pressure and flow equal to 80 horsepower, then we say the efficiency of the system is 80%. This means that even in a well-maintained system, the input power requirement will always be higher than the power required for the work being done. In other words, efficiency will always be less than 100%. However, the efficiency of a system can very often be improved. Let's look at a system to see how that can be done. Suppose we need to move a cylinder to a workpiece quickly, then slow it down as the tooling feeds into the workpiece. This system requires a 50 GPM flow to rapidly advance the cylinder. When the cylinder rod hits the limit switch, it closes a solenoid valve and forces flow through a pressure-compensated flow control valve set for 3.7 GPM. This new flow rate slows the cylinder movement down to the required feed rate. The system's relief valve is set for 1500 psi. One way to get the required flow rate and pressure is to use a positive displacement pump designed to deliver 50 GPM at 1500 psi. To calculate the horsepower required, we can use the formula we learned in an earlier lesson. Multiply the flow, 50 GPM, times the pressure, 1500 psi, times the constant, 0.000583. The answer, 43.7 horsepower, is the power required of a system operating at 100% efficiency. However, suppose the feed portion of the cycle is 2/3 of the total cycle time. During this time, only 3.2 horsepower is required. This means that for 2/3 of the total cycle, most of the power, 40 horsepower, is being dumped back to tank. To increase efficiency, we can use a double pump in a high-low system like the one we saw in an earlier lesson. One side of the pump has a capacity of 45 GPM, and the other side has a capacity of 5 GPM. In addition, we will need to add an unloading valve. Both pumps together deliver the feed rate required for rapid advance. But when the feed portion of the cycle starts, pressure builds up and the unloading valve dumps 45 GPM back to tank at a very low pressure. Horsepower during the feed cycle is just 5 GPM times 1500 psi times 0.000583, or 4.4 horsepower, plus the horsepower required to dump the excess flow to tank. Even more efficiency can be achieved with a single pump, provided it is a pressure-compensated pump. Since the pump still has a 50 GPM capacity, it still gives the rapid advance required. However, when the feed portion of the cycle starts, the pump delivers only what is needed, 3.7 GPM. The horsepower delivered to the system is 3.7 GPM times 1500 psi times 0.000583, just 3.2 horsepower. Pumps with dual compensators can boost the efficiency of a system even more. For example, suppose the system we have just seen required an idle time after the feed portion of the cycle is complete. If the pump had a main pilot spring value of 200 psi and the pilot valve was adjusted for 1300 psi, then the pump would be fully compensated at 1500 psi, delivering just 3.7 GPM and 3.2 horsepower to the system. However, if the auxiliary pilot valve also has a 200 psi spring, then energizing the solenoid during the idle time between cycles will fully compensate the pump at just 400 psi. Horsepower will be 3.7 GPM times 400 PSI times 0.000583, less than 1 horsepower delivered to the system. In this lesson, we have seen 3 of the most common hydraulic pumps used in industry, and we have seen how their operation can be matched to the work being done. In the next lesson, we'll take a close look at hydraulic motors.